This lab is going to deal with some water pollution concepts, including things that we're going to just study kind of out of some tables, and we're also going to do some hands-on lab testing of both things for water quality, like drinking water that we come into contact every day, and also some chemical tests on water from the Passaic River and some groundwater in the area. Water in general is one of the most precious resources on the Earth's surface. There's only 1% of all the water available on Earth is actually fresh water that we can use for drinking and manufacturing. Most of the water in the surface of the Earth is tied up in the oceans, which are salty, about 97%, and only about 2% is in ice in the glaciers in Antarctica and Greenland. The rest, 1%, is what we actually use. So it's very critical that we try to keep our water supplies clean and safe for human use. And pretty soon, a liter of water, just think about what you pay for a liter of bottled water versus a liter of gasoline, which is 1/4 of a gallon. And you only pay about 50 cents for a liter of gasoline and probably more than $1 for a liter of bottled water. Now, there's a number of potentially toxic materials can end up in water. These are both organic, which organic generally means that they have carbon and hydrogen bonds in them. Things like gasoline is organic, and toluene. And then the other pollutant source can be trace metals, things like lead and zinc and chrome and arsenic and so on. Now, all trace metals are actually really important for most life on Earth. You all take vitamins and minerals, or you've heard that certain trace metals are actually good for you, like selenium. And in trace quantities, all of these metals are important. Humans have evolved with a small amount of these materials in naturally occurring rocks, and we actually need them. But the problem comes when we try to concentrate them through manufacturing or mining, where we get an excessive amount of these trace metals in one place, and many of these trace metals have toxic effects to our nervous system, to our kidneys, to our muscle tissue, and so on. So it's real critical to understand both the behavior and the quantities of some of these trace metals. First thing we have to do is go through a couple of definitions. Now, we call sources of pollutants as either point sources of pollutants or non-point sources of pollutants. Now, a point source of pollutant actually comes directly from the discharge from either a manufacturing plant, or the discharge from a sewage treatment plant, or discharge, we'll say for the sake of argument, if we know of a certain landfill that's leaching materials, we'll call that a point source for the sake of argument in this class. In contrast, a non-point source is something that comes from over a wide area. Now, this could be in the case of some cities that have a separate sewage system that's for household sewage versus a storm sewer system. Water that's just in the storm sewers will come from runoff on roads. So that's an example of a non-point source because it comes from a wide area. However, in New Jersey, you have combined sewers, which both the sewage treatment water and the street water get put together and processed through a sewage treatment plant. Where we run into trouble sometimes in New Jersey when the sewage treatment plant can't handle all of the water that's coming from the rainfall, that we have what's called combined sewer overflow. And I'm sure you've heard of situations when that's happened. And essentially what happens is raw sewage is going out into the rivers. And that probably happens in the Newark area at least once a year. Other non-point sources could also be derived from, like, the deposition from the air, such as acid rain. Another possible would be ash or contaminants that are in airborne dust. Or in a large area, say a farming area, there might be pesticides and fertilizers that are coming into the groundwater system, but you can't really define exactly where they're coming from. So those are all examples of non-point source pollutants. Okay, so now let's go over a few of the kinds of pollutants. First, we'll talk about the inorganic pollutants, and those are the pollutants that are essentially the trace metals, or the small amounts of metals that in high concentrations can cause damage. Now, most of the trace metals that we use obviously are used for a lot of things that we manufacture. An element that's not particularly a trace metal, iron, is used in steel, but a lot of trace metals that are associated with steel are things like chrome and zinc and molybdenum and lead, nickel. All of these are kind of associated with the ores that are used to make iron, so there's a source. Pesticides commonly use materials like mercury and arsenic, or they did in the past. The old pesticide, those are poisons in high enough concentration, and you put that on the ground and you're going to kill insects. And this is what was used back in the 40s and 50s, and there's a lot of residue of those pesticides in parts of New Jersey. Gasoline, you wouldn't think of gasoline or oil-producing type products to have a lot of trace metals, but almost all motor oil has all kinds of trace metal additives to help with lubrication and to help with the shelf life of the oil. Things like zinc and vanadium and again, some lead and molybdenum, to name a few. Heavy metals, particularly cadmium, lead, and mercury, tend to accumulate in fat tissue. And just the fact that these things accumulate into an organism is called bioaccumulation. Now, what can also happen with some trace metals and even some pesticides is that they can, what we call biomagnify, which means that if you start with a very small organism, like maybe a plankton or a diatom that's floating around in the water system, and it's eaten by, a bunch of those are eaten by a bigger organism, and then like a midgefly larva, and then that larva is eaten by fish, and the fish eats a bunch of those, and then we go and eat the fish. Well, by the time we go eat the fish, there's too high a level of perhaps mercury in that fish tissue. And that's why even in New Jersey there are a lot of restrictions on the amount of fish you can eat, partly because of trace metals like mercury and lead, and partly because of organic materials like PCBs. There are two tables that show some typical trace metals that are associated with various mining or manufacturing industry. And then there's also trace metals in glass that help give certain properties. The fine crystal, you've heard of leaded crystal, that gave it such a beautiful reflection was because it had this heavy metal lead in it. And there's actually been cases of people that have had so much lead leaching from their crystals that they've actually had a little bit of nerve damage. The other source of trace metals is common in what's called landfill leachate. Again, landfill leachate is the residue of liquid produced when water percolates through the landfill and picks up all these kind of dissolved solutes in the landfill. It could be organic and it could be trace metal. It sort of has the consistency or looks kind of like a dark colored tea. Well, there's a lot of trace metals that are associated with landfill. I should point out that the terminology is used is called parts per million. And a part per million means that there's one part of the substance in a million parts of the material that's containing the substance. Part per million would be 1 gram of chrome in a million grams of rock, for example. That would be a part per million. The second class of potential pollutants are organic compounds. And again, these are usually the things that are pollutants are the things that we've actually manufactured to do a certain job. For example, the organics that are associated with pesticides and herbicides, we manufacture those to basically kill things or to at least inhibit growth. Again, we take original oil material, fossil fuels, and we refine it to make different products like gasoline and diesel fuel and home heating oil. And all gasoline or fossil fuel is ultimately used to make plastics. And to make plastics, we often add hardening agents like chlorine compounds to make polyvinyl chloride. PCBs were manufactured because they were a very good coolant. PCBs are polychlorinated biphenyl compounds. That means they're organic material, but they have chlorine associated with them. And it turns out that organic matter plus chloride can also often be a carcinogenic material. These were used in old oil transformers, and there's a lot of those. You may have heard of the pollutants that are in the Hudson River from the GE plant upriver, and the PCBs that were associated with the GE plant who made a lot of these transformers and the cooling oil that went with them. Cleaning solutions are another potential source of contaminants. Carbon tetrachloride is now banned, but it was a common cleaning compound. And again, it's a carbon-chlorine compound, and it's the chlorine-carbon mixture that can be carcinogenic to systems. There's another class of compounds called volatile organic compounds. These are also associated with aromatic organic compounds, and these are the compounds that are things like benzene and toluene and xylene. And any of these compounds that have an "ene" on the end of them tend to be potential problems as being carcinogenic. I just want to point out that we included a table of some of the bad effects that can happen with some of these organic compounds. Things like mutations are common, like for birth defects. Carcinogenic means that it's cancer forming. and some of them just affect your nervous system or can contribute to liver disease. The last thing I want to point out in the lab is just the table on page 4 that has some of the standards for New Jersey drinking water. It says potable drinking water. That means you can actually drink it. And this is for groundwater that if you were to pump it out of the ground. Now, some of you may live far enough out in the country that you may have some well water, and either you or your parents have probably had a well test. And this is just the kind of information you would want to know if you were going to buy a house out in the country, for example, that had a well. Now, these limits, again, are in very small amounts of parts per million, and obviously these are what's acceptable in drinking water. We're going to do some tests that in river water, and obviously surface water and river water can have a higher concentration of these compounds. And again, I've tried to associate most of those compounds with possible sources in this table. So here's another source of information for the sources of some of these compounds. The things that we're going to actually test for in the lab that have to do with drinking water quality are near the top of the page. We're going to test for total hardness, which has a standard of about 250 parts per million. And we're also going to test for chlorine, which is not shown on here, but essentially we're going to find out how much chlorine is present in some of our waters. The first part of the lab today will be that we're going to look at a map that includes the greater Newark area, including the location of Rutgers. And you'll see that the Passaic River flows basically through the center of the map. And along the Passaic River, if you've ever driven up Route 22 to the north or driven across the Pulaski Skyway, you've seen all kinds of industrial sites and buildings and so on. And there's a whole series of things like gas storage facilities. And in the past, this area was a big site of manufacturing of all kinds of chemicals, paints, herbicides, pesticides, chemical dyes of all sorts, even some munitions. In addition to all those chemical facilities, you'll notice on the far right of the diagram is kind of a lot of open space. Well, it turns out most of this open space is actually sanitary landfills or basically municipal waste. Some of them are hazardous waste landfills. Also in the vicinity of Kearney and Harrison, there was a lot of chrome manufacturing sites during World War II. A lot of chrome ore was processed here in Newark, specifically in some sense for World War II ammunitions. So there's all kinds of potential sources of pollutants that have leached off the surface of the ground here in the Newark area. It has ultimately found their way into the Passaic River, aside from the stuff that's coming farther up north from other sites. So the first task that you're going to work on is just based on the information that I gave previously in the lab about what sorts of pollutants are associated with various industries. We're going to just select some of these that are along the Passaic River and just have you put in several, up to 4, I guess, in each category of what kinds of pollutants might come from each of these kinds of facilities, and list several items that might be a pollutant source that come from each of these things. Also, we're going to ask you to list some non-point sources that might contribute to the Passaic River, and these are the things that are going to be falling on the land surface in general and be washed into the river itself. The next part of the lab, we're going to do some chemical testing using test kits, again, that are manufactured by Lamont Chemical Company. And again, these are tests that you might perform out in the field just if you're trying to do something on a reconnaissance basis. Obviously, they're not accurate enough for full reporting, to a government agency or whatnot, but they're very good, and environmental geologists and geochemists and scientists use these routinely when they go out in the field. But the first test we're actually going to do is we're going to test the chlorine in tap water from Smith Hall, and we're going to see if the Brita water filter, or a similar type filter, not to push this one brand, but whether these filters actually remove chlorine as they claim they do. So we're going to just try that out. So first thing is we'll have this test. We'll use a small vial, and all of these are numbered, and they're numbered also in your lab handout. Make sure that you follow the directions because we have several different vials and there's going to be a lot of different tests. So this one is number 0230. Okay, and we're going to fill that vial up to the black line that's in here using this tap water, and it's probably easiest to use a dropper of some sort. There's several different kinds will be available. And then we're going to add one of these handy dandy tablets that is going to indicate whether there's chlorine in here. And all of these tablets and reagents that we use are basically have some kind of color dye similar to what you used in the soil test kit, or will be used in the soil test kit, that reacts if there's a certain percentage of that chemical in the water. So we're going to just add this tablet. It's pretty easy and straightforward. You could even probably talk your tea into taking one of these home for you to test your own water. But what we'll do is we'll put the tablet in, shake it up a bit, let it sit for a few minutes. You can already see that we've got quite a pink color developing. We're going to take this device called a comparator that, again, is just got some colors in it that this one goes down to 0.1 ppm and this one up to 0.4 ppm of chlorine. And we're just going to compare our tap water with this range. And essentially, when you start getting up to 0.4 and above, you'll be able to taste the chlorine. And I'm sure that many of you have tasted chlorine in our tap water, and I certainly do at my house. But anyways, it looks like that when I look at this, that it is really pretty close to the upper level of this, okay, in Smith tap water. The next test we're going to do is actually for hardness of water, and we're again going to use the Smith Hall tap water, and we're going to compare it to some locally and not so local brands of bottled water that are commonly drunk around. And hardness is essentially how much calcium or magnesium carbonate is present in the water sample. And hardness tends to make the water taste a little bit, I call it tastes like a basement, but it tastes a little bit musty perhaps, or it has kind of a little bit of a chemical taste. And hardness also is bad for some manufacturing. When you have a lot of extra calcium or magnesium carbonate in there and you're trying to make something that's ultra pure, you don't want to have those solutes present. It also will leave a scum on water on some of your appliances at home if you have too much calcium or magnesium in the tap water. It kind of leave a soap scum and makes soap a little bit harder to use. So typically, if you have really hard water, you install a water softener, which actually exchanges sodium or sodium and potassium for the amount of calcium and magnesium that's present. And again, sodium and potassium make the water a little bit more slippery, and it doesn't have quite the effect as calcium and magnesium. So what we're going to do then is just try to test this water, and we're going to compare it with some of the common bottled waters. Now, again, hardness is not harmful to you. It just really is a taste, or particularly in manufacturing, when you want really pure water, you don't want to have a lot of hardness. But again, it's not harmful. So the first thing we're going to do, again, is take the Smith tap water, and again, this time we're going to use this. It's a DR titrator bottle, and it's number 0769. And it's got a white line that is marked at 12.9 milliliters. And we're going to fill our bottle up, again, using probably the syringe is the easiest way, because I always overshoot if I try to pour. So, well, maybe I'll give it a pour. Yeah, that's pretty good. It doesn't, again, have to be exact, but I could do a little bit better. Okay, so you want to fill it up just to the line, and if you remember anything from a chemistry class, perhaps, you'll know that you want to try to get the lower part, the curved part of the water about where the line should be. That's called the meniscus. Okay, so then we're going to take this, and it's important again to read your directions on this lab, on this part, because there's several tests to be made. You're going to want to add 5 drops of this hardness reagent 5, and your TA will probably assist you with making sure you keep everything straight. So add about 5 drops. Okay, and then we're going to add one of these, again, an indicating tablet that's going to test for the total hardness that's present. That's going to be the sum of calcium and magnesium hardness as calcium carbonate. And it's going to turn a nice, pretty bright pink, but it's going to take a second to dissolve. Okay, while we're still waiting for that to dissolve, the next thing we're going to do is we're going to end up adding another reagent, and this is actually called a titration. We're going to add drops of this. It's really like an acid-base titration in chemistry, but we're going to add drops of this, and this indicator, which is just a pH indicator, is going to change color when we get to the point where this reagent exactly matches the amount of total hardness, that's calcium and magnesium, in the vial. So this vial has a hole in it, and you're going to fill this up just like you would at the doctor's office with a shot. And you're going to pull the plunger back so that the bottom of the little black plunger is right at the 0 mark. And you'll notice that there are lines on this kind of glass syringe that are from 0 to 200, and this is going to be just strictly converted into numbers or parts per million of total hardness as we put this in. So we're going to put this through the hole in the top, and then just slowly, drop by drop, we're going to add it to the, with a little bit of shaking, we're going to add it to the solution, and it's going to turn a really dark blue. And you can see sometimes, even every time you add a drop, you can kind of see maybe a swirling of blue start. It's going to first turn a little bit purple, but you want to make sure that you do kind of slow because it's easy to go too fast. And it's starting to go. We don't really need to do much more. That's a little bit too purple yet, so maybe one more drop. And there, it's a nice, real nice blue. Okay, so you want to make sure you shake it as you go because otherwise you can overshoot it really easily. Okay, so then you take the plunger out and you look at where the bottom of that little black mark is, and if you have better eyesight than I am, you would see that it's at about 76. So that means we have 76 parts per million total calcium hardness, or calcium carbonate hardness. That's the total hardness. Now we're going to do the next step, which is going to be also test this for the calcium hardness, and then we'll figure out the magnesium by difference. So the next step is going to just do the calcium part of this hardness test. Now, hopefully, if we already measured the total hardness, hopefully our results will come out with calcium being less than the total hardness. But we have to start with a fresh sample of water. We're done with this one, and we have to start with a fresh bottle and a fresh sample of water. Okay, so I'm going to pour again and see if I can get it close. A little too much, so now you take your syringe and go the other way. Okay, now I have to follow these directions myself. Okay, so this time we have to add 6 drops of the sodium hydroxide indicating solution. That's different than we did the last time, so we have to add that first before we add any indicating drops. So 3, 4, 5, 6, and we'll swirl that around a little bit. And then we're going to add a calcium hardness tablet, which is in a different vial. And again, your TAs will make sure that you get these straight. But again, it's a calcium hardness tablet. Has a slightly different chemical constituency, so it gives a different reaction. But essentially, it's going to be the same. It's going to turn a pinkish color. And again, we'll shake that up. Now the other thing that's real important is you want to go back and refill your syringe all the way up to the 0 point again, so we can start this completely over. Okay. Remember that our last result was about 76, and it's going to vary a little bit between groups, but this one hopefully will be less. And see, it's already starting to turn purplish with just a few drops. Pretty slow. And maybe one more. There we go. And again, it's very similar to the blue we had before. And now we're going to look at this, and lo and behold, in my poor eyesight, it reads about 50. Okay? So it is less, which makes sense. So we say that the calcium hardness is 50 parts per million, and the magnesium would be done by difference. So that's just an example using the Smith Hall tap water. We're also going to have you test, depending on the group, various bottled waters, just for your own interest to see what the hardness is of those. So now that you have your numbers for the total hardness, calcium hardness, and the magnesium hardness by difference of the Smith Hall water plus any other bottled water that you might have analyzed, we're going to compare those numbers to the table that's on the next page of your handout that kind of lists the ranges of hardness. And again, if the total hardness is somewhere between 0 and 60 parts per million, then we consider that water to be relatively soft, and it doesn't have very much calcium or magnesium carbonate. On the other hand, if the water is greater than 180 parts per million, we consider that very hard, and that would leave residues when it evaporates, like on your faucets, and it might taste a little bit earthy. So now with those numbers in mind and your analyses that you just made, we're going to ask you a few questions, such as which of these water samples might have been in contact with limestone or dolomite type rocks, calcium carbonate or magnesium carbonate type rocks. and which samples might have come from rocks that had more igneous or metamorphic, where you would expect to have a lot less of calcium and magnesium in the water. Okay, we're going to do 3 more tests, and basically on some waters from the Passaic River area and also some groundwaters associated with a chrome processing plant. But essentially we're going to measure some pollutant levels in these waters. And the first test we're going to do is to measure cyanide. Now, cyanide is a compound that is definitely manufactured. It's not necessarily found in nature. It's a CN compound, and it's commonly a pollutant in many manufacturings that use any kind of metal plating or electroplating type things. And it's actually quite common in a lot of our rivers. So the first thing we're going to do is just take our sample of Passaic number 1 sample, which sort of has some algae growing in it, but that's okay. A little bit green, but that's all right. And we're going to fill up this smaller vial that you have in your kit up to the rim, essentially. And again, it's probably best to use a pipette because you won't spill the water around. And probably one more. Yeah, a little bit. Okay, right up to the neck. And then we're going to add, let's see, 1 drop of the cyanide reagent 1, which is this blue colored material. And just a drop is all we need. And similarly, we're going to add just 1 drop of this, again, this cyanide reagent 2. This one is the one that actually is going to change to a pinkish color if there's cyanide present. And even though I filled this up full, we really only need 1 drop. Put the rest back and close everything up. And we really have to let this shake or sit for about 5 minutes, and it should turn some light pinkish color. And what you're going to do then is take that sample and compare it to the set of standards that have been made up in the class by your lab assistants. And they basically correspond, again, from 0 parts per million at the lightest shade of pink to about 4 parts per million at the deepest. And that's just going to be your kind of quantitative estimate of how much cyanide is actually present in your sample. Our next test is going to be for chrome 6 actually, in 2 samples of groundwater that were collected near the Kearney area. And again, we'll use these 2 samples of groundwater, and we're going to test again for chrome, similar to how we did it just the last time. Again, we'll take our bottle. We're going to use the same vial that we used for the first test for chlorine, and that's again number 0230 with the black line. And again, fill up the sample up to the black line. And again, you want to get it as close as you can to the black line. Set that aside. And then either your TA or you can go ahead and do this again. This is just a powder that contains, again, another reagent that's going to change color. And again, it's going to be pink. There's a lot of pink in this lab. But we'll, again, your TA will add it for you. And it's kind of a little messy. The top on, and again we're going to let it shake for a while. And it'll take a few minutes for the full color to develop, and also a little bit of time for this to dissolve. And so while we're waiting for that, I'll show you, again we're going to use one of these color comparators. Again, just make sure you use the one that's labeled chromate. And again, we have 2 colors, kind of a light pink color that corresponds to 0.5 parts per million, and a darker pink color that corresponds to 2 parts per million. And again, we're going to just compare between those 2 extremes. Here we have the sample in the color comparator, and it's a little bit murky, but nevertheless, I think you can see that it's it's closer to the lighter pink color, so it's closer to the 0.5 than it is to the 2 parts per million. And I would say it's probably just a little bit higher than the 0.5 parts per million. So there's the example of how you're going to do that test. Now you'll go ahead and test the other water sample in class. Okay, the next and final test will be for nitrate in the river water. And again, these water samples came from 2 different locations in the river, one downstream from the sewage treatment plant and one upstream. And I'm going to test one of the samples, but I'm going to turn these around so you don't know which one I'm testing. The vial that you're going to use in this test is going to be this, the last vial that hasn't been used so far. It's got 2 white lines on it, one marked at 2.5 milliliters and one at 5, and it's vial number 820. Okay, and we're going to fill up the sample to the first white line. Okay, and then we're going to take this material called mixed acid reagent, fill it up to the second white line. And this is a very, very dilute acid that was going to remind you of pickle juice. And your TA will probably do this for you. And we're going to want to put one of these lids on and just give that a swirl. And then we're going to add the indicating powder again. And this one is nitrate reducing agent, it's called. And this is going to actually take the nitrate that's present there, and the amount of color change is again going to be proportional to the amount of nitrate that's present. And again, your TA will probably add that tip for you. And it'll take just a few minutes again for the color to develop. Now while we're waiting for that to develop, I'll just show you again the comparator that we're going to use. And again, it's very similar to the others we had, only the numbers are different. Again, make sure you use the one that says nitrate. We're going from a low of 2 parts per million with the light pink color and a high of 10 parts per million in the dark pink color. And again, when things are above 10 parts per million, that's unsafe for drinking water. Obviously, river water can have a much higher concentration, so not to worry if it gets this high. Nevertheless, this is kind of the range that we're going to be dealing with. Okay, so now that I think our color is developed sufficiently, so I'm going to go ahead and put it in the comparator. And it looks like this sample is pretty high. And it's definitely not as low as 2 parts per million, and it's definitely not as high as 10, but somewhere in between. You might just call it halfway, about 5 or 6. And now you're going to test the other sample and try to tell us which one is downstream from the sewage treatment plant.